All right. Still good on volume? Okay, so today we're going to talk about reinforcement learning. And a lot of the machinery we've seen in MDPs was actually to set up what we're going to do today and in the next lecture. So we'll be seeing our values and Q values all over again. So reinforcement learning in some sense is a very basic thing. You would like to teach some agent to act in an optimal way, and you do that by allowing it to try various things in the world and receive rewards. Of course, the idea is you're supposed to act in such a way as to receive more rewards, and this slowly shapes your behavior. But it turns out that although we can formulate it very simply, solving the reinforcement learning problem is very hard. And although we're going to make some progress on it in the next few lectures, we're really just going to scratch the surface. Some of these ideas will come back later in the course in new contexts. So what is reinforcement learning? The basic idea is you have an agent that receives feedback in the form of rewards. And when you think about these rewards, you should think exactly as the rewards were in an MDP. Every time you take an action, you get a reward back in return. And so the flow chart you can see here is that you have an agent, and the agent takes actions in a certain state. Okay, so that's just like an MDP. And then it's the environment's turn. So you take an action, but you don't actually necessarily know what the action is going to do. In an MDP, you didn't know what the action was going to do because it was uncertain. There are multiple possible outcomes, and they have probabilities attached to them. In the reinforcement learning context, you also don't know what the possibilities are until you experience them. So there's actually two kinds of uncertainty folded into one here. But you take an action, and then you can imagine the environment responds. And the environment responds with one, a response state, that's the result of your action, and two, a reward. So you land in a state, and you get some immediate reward. The agent's utility is defined by the reward function, just like with an MDP. So your goal is to maximize the rewards, and that there may be a discount associated with them. So you want to learn to act so that you maximize the sum of expected rewards. All of the learning that you do, therefore, is based on what actually happens. So, of course, you can't know when you take an action and you land in a certain state what else might have happened. The only way to learn what else might have happened is to try it again and see if you get some new outcome. So in this whole context of reinforcement learning, all the learning is coming from the samples that we experience. And your experience might be typical or atypical or lucky or unlucky. And so there's another layer here of expectation. You're not actually sure what experiences you're going to have. So let's see an example of reinforcement learning in the real world. So if you'll remember these Aibo soccer robots, we saw them primarily in the first lecture as an example of how if you have a robot, if you have a dog-shaped robot, you might not want to kick a ball like a dog does, but rather do some weird plastic robot way to shoot the ball. Now we're going to look a little bit more about how these things even move around in the first place, right? You could look at this robot and say, okay, I know how it should move, right? It should kind of move one leg forward and then the opposite leg in the rear, and then you could kind of try to write down a movement function, but it would turn out to not work very well. So what we're going to see here is a dog starting with a kind of initialized policy, which more or less moves it forward, trying over and over again to kind of try variations of that policy, and its reward has to do with how quickly it makes progress and also how stable the video is. And that turns out to be important for vision that's being done on that as it plays soccer. So let's take a look here. This is from Peter Stone's lab at Austin. So take a look here. This is the initial gait. You know, it's more or less how you might think a robot dog would move, but you can see it's slipping. It's not super efficient, but it's making forward progress. This is the initial policy. Now, as it's going, it's getting rewards when it moves forward. One thing to note about walking is sometimes you go faster and sometimes you go slower, and there are parts of the gait where you're actually slowing down even when you're doing the right thing. So, of course, it's not about acting in a way that gives you the next instantaneous reward. It's about acting in a way also that sets up future rewards. So that's the initial gait. And so then it trains and it walks and it walks and it walks, and it starts to get a little better. And this is through reinforcement learning. So when the variations that led to better rewards are then used to shape the policy, and now you can see it's much more efficient. And then all of a sudden you've got an Olympic caliber Aibo here. Now, you might think the reward function should only have to do with moving forward. And if you set the reward function to only move forward, you might be able to move forward faster. but of course you might then be kind of shaking around, which makes the computer vision to track the ball hard. It's hard to play soccer when there's an earthquake on, right? And that's what it looks like when you move in an unstable way. And so if you balance the rewards to also take into account stability, there's a trade-off. And the idea in reinforcement learning is you specify the rewards, and the learning then makes the trade-offs for you, and you end up with different behavior based on the utilities that you prescribe. Okay, so that's learning to walk. Here, let's see another example. A lot of these reinforcement learning kind of videos, classic experiments, have to do with some kind of walking. There actually are some deep reasons for that, but plenty of reinforcement learning has nothing to do with walking a robot around. This one, however, this is out of the MIT lab. This is an interesting example, aside from the fact that this robot actually kind of looks like a toddler in general shape. This is an example of the ability to walk partly being in the control policy, but also partly being in the hardware. So with the kind of human body, we have to learn how to walk, but partly our bodies are designed to move in certain ways that facilitate walking. And you can see the same thing here. This robot is pretty stable, and so as you kind of walk around, it kind of toddles around, and it doesn't always move in the right direction, but it doesn't really have to worry quite so hard about not falling over unless it does that. And next thing you know, it's kind of more or less heading in some direction like a toddler might, and it's making more forward progress. And then next thing you know, it's kind of moving purposefully forward. And then I guess it's off to college. So there it goes. Okay, so how do we do these things? Well, let's take a look at a slightly simpler robot. You'll grow to know and love this robot because this is your project 3. So here he is. I call him the crawler. Now, if you ignore the fact that his body, aside from the rectangle, is basically a giant spike, he's actually kind of cute. So this is about the simplest robot. This is in 2 dimensions, right? There's physics here in the sense that this is in simulation. There's physics in that it doesn't float off into the air or anything like that. But really, there's only actually 2 arms here. So there's the yellow arm, which is actuated kind of at the shoulder, and there's the red arm that's actuated at the elbow. And this thing has to move forward. Now, when you're this simple robot, you can basically only do it by stabbing in front of the ground and lurching forward. So it's not, it's not a design necessarily favored by nature. But what's going on here? So what you can see going on here is it's trying a bunch of stuff. And most of what it's trying doesn't actually make progress. This is exploration. It doesn't know what's going to work. It's trying a bunch of stuff. You look at this and you think, okay, well, I could do better than that. And you probably could. I could stop this thing. Let's do it. I could stop this thing and I could say, okay, you're going to lift this arm and you're going to go this way and then down. And then, I could try to give it a demonstration. And there are, in fact, reinforcement learning algorithms that operate using demonstrations as a valuable source of training. But here, basically, it's going to explore around and in the interest of not spending the whole lecture watching it flail around, we can skip a lot. So, now it's like tomorrow or something. And I'm going to change something that I'll tell you about later. And you can see that it's now basically learned how to walk. Cute, terrifying, you be the judge. Okay. What's cool about reinforcement learning is that it's learning how to make kind of forward progress, where forward here means to the right, but there are parts of this walking cycle where it gets no reward at all, right? It's just setting up future rewards. And that's because the definition of the problem has to do with maximizing the sum of future rewards, not instantaneous rewards at that exact time step. Otherwise, it would just kind of sit there and kind of jiggle back and forth trying to get instantaneous rewards. Okay. Let's stop that. One cool thing in the context here is that the only reason it chooses to go in that direction, I didn't tell it how to walk, and I didn't tell it I didn't tell it how to walk, and the reason why it even walks to the right is because that's the direction the reward says. So if I, for example, invert the reward function, what do you think is going to happen? Let's skip a million steps. And there he goes. He can just as easily learn to go the other direction based on the rewards you give. So this is, again, an example of utilities or inputs, but the actual behavior that's computed is just going to optimize whatever you asked for. Okay, you'll build that for project 3. Okay, Any questions about the setup? Okay, it's not all going to be robots walking. In fact, you will also get a chance to do reinforcement learning for Pac-Man, which we'll see in next lecture, how that's going to work. But let's talk a little bit about formally what is a reinforcement learning problem. And the answer at the bottom level is it's an MDP. So formally, we imagine there is an MDP. And you say, I know how to solve MDPs. I do value iteration or I do expect a max search. And if you knew the MDP, you wouldn't need reinforcement learning. So there's got to be something different. There's still a set of states, just like an MDP. There's still a set of actions, which can depend on the state. And there's still going to be a model, that is, each state has some non-deterministic result, and there's still a reward function. We're still looking for a policy that's going to maximize the sum of returns. The new twist is, for example, look at this car MDP here, that we know there's these states, there's these actions, and we know that each action does, for example, 50% chance of staying in the same state, 50% chance of cooling down. There are various rewards. We needed those in order to run value iteration. Okay, basically, those are gone. So the new twist is we're in an MDP in which there is a transition function and there is a reward function, but we don't know what they are, or at least we don't know what they are until we experience them. Okay. So the difference is, rather than just planning offline on the basis of a known model, we now have to try things out in order to figure out the rules of the world we live in. And that means we're going to make mistakes, and it means we have to think about things like, how often do you try something that looks bad before you give up on it? So there's going to be new kinds of trade-offs that we saw a little bit at the end of last lecture with our casino experiment. Okay, important distinction, because it's very easy to confuse these, and it's especially easy to confuse because when we talk about the real world versus in simulation, and you have a robot, it's obvious, right? The real world is when you actually have to plug it into the wall, and this, it actually moves around. And in simulation is when it sits there and smoke comes off the CPU, right? Whereas when you're talking about Pac-Man, what's the difference between the real world and simulation? It's like whether or not you call game.getSuccessor or something like that. So it's a little bit subtle. So that's why we keep pushing on this distinction between offline and online learning. Okay. Offline solution, that's what we did with MDPs. The idea behind an offline solution is you're sitting there, you're in the real world, but before you do anything stupid, you're going to think about your consequences. So you can think, all right, should I move off to the left here? And you think, you're like, okay, I know probably I'm going to move to the left, then I'm going to receive a negative reward. I don't like negative rewards, so I'm not going to do it. Okay, the falling into the pit and suffering happened in your mind because you knew it would happen. You didn't actually do it. Okay, in online learning, okay, it's more like, should I move to the left? I don't know. And then you try it. So one big difference is when you do online learning, you break a lot of robots, right? You'll actually see more about this when we talk later. Peter will talk about some of his helicopter work. You break some robots. So definitely the kind of dollar cost and pain cost in terms of robot pain is higher for online learning, but you have to do online learning unless you already know how the world works. And so invariably, you need to do a little bit of both in the real world in order to solve problems well. Okay. Now we're going to talk about ways in which you can do reinforcement learning, which means how you can decide how to act when you don't know what the transitions and rewards in your MDP are. And most of what we're going to talk about is something called model-free learning, which we're going to get to in a few minutes. But first, I want to basically sketch an alternative, because the alternative is a little bit more related to things we've already seen. So the alternative is something called model-based learning, and a lot of people do this. So in model-based learning, what you do is you say, all right, I don't know the MDP. If I knew it, I could solve it. So my priority is not actually learning how to act, it's learning the MDP. Once I learn the MDP, I'll just run value iteration and do what it says. Okay, so you construct a model of the world, and your learning is for building a model, not for valuing actions. Okay, so that's the model-based idea. You're going to learn an approximate model. It's going to still be based on your experiences. So there's a kind of subtle distinction here. Then you're going to solve for values and policies as if the learned model were correct, which it's not, right? So this won't be perfect. Okay, step one is to learn the empirical MDP. Well, there's a lot of details in how you could do this in the most efficient way, but here's one way to do it that, broadly speaking, would work. So you act in some way. You try a bunch of stuff. You jump off a bunch of ledges in the grid world. And for each state and action, you've tried them a bunch of times, and you have recorded what happened. And so you know, okay, when I moved left, I always ended up in the pit. When I moved right, I ended up at the exit, and so on. And so for each S and A, okay, what's S is a state. What's SA? SA is a Q state, right? It's a state action pair. For each SA, I know the things that have happened in the past, And I just say, you know what? That's the transition function. So I normalize that. That means if one state happened once and the other state happened twice, I say the first one has 33% and the second state has 67%. I normalize them so they add up to 1. And I say, that's my transition approximation. The little hat means empirical here. Similarly, for every state action S prime triple I get, when I experience it, I get a reward back. And we imagine the rewards are deterministic. There's fancier versions where the rewards are non-deterministic too, but we write down R as we go, and we build an approximation to T. And so now I've got this it's like this. You've got something that looks a little bit like the truth, and the more time you spent collecting data, the more it's going to look right, and then you solve that. So step 2 is you just run value iteration. And this is basically fine. Okay, if you spent enough time in step 1, this would work. But it's going to be a little bit tricky to know when you're done with step 1 and when you should switch to step 2. And we're going to prefer methods that we're going to talk about soon where you're constantly learning and everything you've learned so far feeds into your actions. So we don't always want this division between a learning phase and an action phase. Okay, but that's the idea. Learn a model and then do what you would have done last week with that model. Questions? Okay, let's see an example of that. So here's an input policy. Okay, if you're going to be learning, you're going to need an input policy. Often the policy you learn with needs to be a random policy, which means rather than having one action you recommend, you have to maybe roll some dice to see what action you're going to take, because you're only going to learn about the things you do. And that's going to be a recurring theme in reinforcement learning. You learn about the things you do, so if you want to learn about everything, you kind of have to eventually do everything. But let's imagine there's this input policy, and we're going to do some model-based learning. Well, imagine gamma is 1, and we're on this grid world, and so we do some training, okay? And I won't walk you through each episode, but the first episode, you're in B, you choose to go east, you happen to land in C, you get a -1. You're in C, you choose to go east, you happen to land in D, you get a -1. You're in D, you choose exit, you go to the terminal state and get a +10. Okay, that was episode 1. Then we do episode 2 and episode 3 and episode 4 and so on until we're satisfied that we've got enough data, and then we move on. So what we have to do when we move on is we have to say, all right, on the basis of all of that evidence, what happens when I go east from B? And I would look, and I'd say, okay, well, I did it here, and I did it here. I guess those are the only times. It looks like 100% of the time I end up at C. So when I learn my transition model, it'll say the transition probability from B choosing east and landing in C, that always happens. Is that right? Probably not, but it's what my empirical data suggests. Similarly, if I go east from C, it looks like we got D once, D twice, D 3 times, and A once. And so we write that down in the transition probabilities. Again, you'd have to do this a lot of times to have much confidence in these numbers. Later on in the course, we'll talk about kind of sampling confidence and things like that. For now, let's just kind of not worry about it. Similarly, we know what the rewards do. So we know exiting from D is worth +10, but we didn't know it till we tried it. Okay? So one problem with this kind of thing is you only learn about the things you try, but there it goes. And then we plug this, this learn model, we send that off to our value iteration algorithm, and now we know how to act. Okay, that's model-based learning. I'm going to draw a distinction that in this example is going to seem extremely subtle, and worse than subtle, it's going to kind of seem uninteresting. Okay, but bear with me here. So let's say I wanted to know the expected or average age of students in this class. Okay, how could I do that? I want to compute an average. And really, if you think about it, everything you compute in reinforcement learning is an average, right? It's average rewards, you're averaging, at the chance nodes, everything's just averages. So we're computing averages, and we're doing it based on samples of experience. So this is a reasonable thing to ask. I want to compute the average age of students in this class without kind of knowing all of the details. So if I knew the distribution over ages, so if I happen to know exactly how many people in the population were of each age, how would I compute the average? Well, I just, sum up all of the values. So here's the probability of each age times the age itself. And that would be maybe 0.35 of the people are 20, and I just kind of continue on adding up all of the numbers. Okay? Everybody clear? If I know the distribution over ages, simple weighted average calculation. Easy. Okay, now what happens when I take P of A away from you? So P of A is gone, right? You don't know P of A, so you can't use this equation. Right? And you can think of this equation as value iteration. It's taking some averages and doing something, and suddenly I've taken away your probability distribution. Well, what I can do is instead rely on samples. right? So I can pick people at random and say, all right, random person number 1, how old are you? Random person number 2, how old are you? And I can take samples out of the class, right? And maybe I take n samples. Obviously, more samples is going to be better, but let's set that aside. I take some samples. Now, the question is, once I've gotten my 30 samples, how do I compute the average age? Okay, and there are 2 answers, and they're exactly the same thing. They're just 2 different perspectives on the same simple computation. So one answer is the model-based way. It says, well, I know how to compute an expectation when I know the distribution over ages. So the first step is figure out the distribution over ages. Okay, how many of those 30 people were 20? How many of those 30 people were 21? And so on. Okay, so in that way, I compute a probability, and then I just reuse my equation from before. Right, I kind of reduce it to the known probability distribution case. Everybody okay with that? That's not the normal way you would compute a sample average. How do you compute a sample average? You just do it. You just take your numbers, your 30 numbers, and you average them together. What's that look like? That's essentially the model-free way, where I just take an equally weighted average of all of the numbers. So I've got my 30 numbers, just add them all up and divide by 30. Okay. The reason the thing on the left works is because eventually your probability distribution gets correct. How come the thing on the right works? Why does it work to equally weight them? Right? And here's kind of the key confusion that we'll hit later, even though it probably hasn't hit yet, which is, why aren't you upweighting the common ages in this average? Right? If there are more people who are 20 than 50, right, why wouldn't I give the 20s more weight in this average? Why don't I kind of count them twice? Yeah, exactly. So this is, it might seem obvious, it might seem subtle, but the key point is exactly right. The things that are common show up more times, so we don't need to upweight them. Everything in this average has the same weight. And although this is clear here, you'll get a little confused by it later when this idea comes back. So everything has the same weight. The frequent things just show up more times. All right. Okay, so samples come with the right frequencies, and things work out. This is the exact same computation, and it's the same thing with reinforcement learning. You're basically doing the same computation. But in the left view, you reconstruct your probability, and your right view, you say, I don't need the probability. I'm going to directly take the average I care about. Okay. And that's going to be our lead-in to model-free reinforcement learning. Is there a question? Yep. Yeah, this is a great question. What happens when your action space is infinite, right? So everything we're going to talk about here is discrete action spaces. When there's infinite action spaces, obviously it's not meaningful to talk about taking all of them many times. You can't even take all of them once. And so in order to work in those spaces, you need to either have a model that's parameterized in some way, so that although there are infinitely many actions, they're controlled by some smaller number of parameters, right? It can't be an arbitrary function from real numbers to real numbers. And then you're in a space of learning those parameters or something. That'll be a little more natural to talk about after next class when we talk about parameterized reward functions. Great question. Any other questions? Okay, so let's talk about model-free learning. In model-free learning, we're going to directly try to estimate whatever it is we care about. Okay, so if we care about a value, we're going to try to directly average the sum of returns, rather than trying to learn transitions and rewards and running value iteration. Okay, so first we're going to talk here about a simple case, something called passive reinforcement learning. In passive reinforcement learning, you don't choose the actions. You're kind of along for the ride. The learner just watches what's happening, right, and has no action selection going on. It watches what's happening, it takes notes, and it writes down what's working and what's not. So in some sense, you're an observer. You're just evaluating what's going on with your clipboard. So formally, it's the task of policy evaluation, which hopefully we'll remember from last lecture. In policy evaluation, the input is a policy. So somebody gives us a policy. We don't have the kind of either the responsibility or the luxury of trying to choose what action is best. We're forced to run this policy. Okay. Our job is to figure out either the transitions and the rewards in a model-based way, or since we're going to be doing model-free, what we're going to do is directly try to learn the state values for this policy, and we're going to do it in some way that is robust to the fact that we don't know TNR. Okay, So in this case, the learner is kind of along for the ride. You have no choice of what actions to take. You execute and learn. It is not offline planning. You're actually doing things in the world and writing down what happens. Okay. Here's our first algorithm for passive reinforcement learning. It's called direct evaluation. It's not a very good algorithm, but it's easy to understand. Since we're trying to compute the value for every state under pi, we're going to run the game a bunch of times, right? And that could mean kind of simulating Pac-Man, or it could mean starting the robot and letting it go for an hour and then doing it again and again. Whatever it is, we're going to get a bunch of plays of the game. And then, after we've acted according to this policy, we're going to say, for each state, we're going to check to see, when I visited the state empirically, what have my returns been? I'll average them together, and that's my answer. So let's see it in action. Here's that same input policy, right? A and D here are the exit states. And now what I do is I say, all right, I'm going to train, just like I did when I was trying to learn a model. I'm just going to do different things with the results. So I have episode 1. In episode 1, I go from B to C to D, and then I exit. And then I go from B to C to D and exit again. And then I start at the bottom. So those were all from B. These are all from E. So I go north, and then I go east, and then I exit, and then I go north again. Okay, so I have all of these experiences. What's interesting, the first ones are from B, the second ones are from E, and usually I exit D and get a plus 10, but in episode 4 I exited from A and I got a minus 10. Okay, so A is the bad exit here. Now, rather than trying to learn transitions and rewards, what I do is I say, what was my job? Okay, my job was for each of these states to write down its value under the policy. Well, let's take an example. Let's take D, right? What's D's value under this policy? Well, I eyeball it and I say it looks like it's plus 10. Okay, what's A's value under this policy? Minus 10. Are these right? Who knows? These are the empirical values. All right, let's do something interesting like C. What is C's value under this policy? I have to find every time I was in C, and I say, what were my scores? Well, the first time my score was 9. Then the second time my score was 9, and the third time my score was 9, and the last time my score was negative 11, right? And so I continue, I take the average of that, and I continue, and I write all these down. Okay, and these are the numbers I'll get. Everybody clear on the algorithm? For every state, I want to know the average returns, and so for each state, I look at my empirical average returns, and I average them. All done. There's something wrong with this algorithm, but any questions on it? Okay, yep. How did I arrive at the numbers? Well, let's say, where did this plus 8 come from? Well, that is the score I get from B. Well, I was in B twice. Once here and once here. The first time I received plus 8. I received plus 8 both times. And so I average those together and I get a plus 8, and that's the reward from the returns from B. Okay? Okay, so what have we accomplished? Well, we've now figured a way to find out the average returns under this policy without knowing the transition probabilities. They weren't relevant. We just found a way to do the computation without them, but in a very blunt way. Yeah, there was another question? Okay, again. Because from E, once you get 8 from here and negative 12 here. So the average of those is negative 2. I might have messed up the math, but that was the intent. Other questions? All right. So we could be done, right? We could end lecture early, right? Why does that not work? Well, what's good about this is it's easy to understand, and it's clear that you were able to do it without ever figuring out T and R explicitly along the way. And those are nice properties. And it does eventually work. Okay, but what's wrong? Well, what's bad is it wastes a lot of information. So for example, what does B do? Kind of we know in our experience B only does one thing. Where does B take you in this policy? It takes you to C. What does E do every time? It takes you to C. Okay, so B and E do the exact same thing. They both always take you to C, and you know this. So what are they doing with different values? How come E looks so much worse? Well, you came from E the one time when things worked badly from C. But it kind of doesn't matter, right? That's a statement about C, and it's a statement about everything that takes you to C as well. But in this method, it only informed us about E, right? Because the experiences from E, even though they all go through C, they don't kind of share information for all of the times you got to C in other ways. Okay, so this -2 is supported by 2 runs through C, whereas really we have 4 relevant episodes. So we waste a lot of information, and that means we've got to run the game many, many duplicate times in order to get averages that mean something. So it takes a long time to learn. So let's try to fix that. Okay. We actually have an algorithm for policy evaluation, if you remember from last class. What's the algorithm, right? The algorithm, we said, well, if we knew the MDP, it would be like doing Expect-A-Max, where you have only one choice of action, but then you have to average all the possible outcomes of your action, right? And we had a way of using a one-step look ahead. We'd start off with value estimates of 0, and then we do these updates that said, my new value estimates from each state are written in terms of, from that state, all the different S primes that could result, and for each S prime, we'd write down a reward plus a discounted future approximation. This algorithm was nice because it took everything we knew from the previous round, and it allowed us to recycle it everywhere where it was relevant. So this algorithm connected all the states up through a one-step look-ahead Expect-A-Max. So in some sense, this is the algorithm we want. Nope. So in some sense, this was the algorithm we want. So why don't we just run this? Just quick sanity check. Why don't we just run this beautiful algorithm? Why don't we, for each state, just do the one-step look ahead, Expect-A-Max, compute this average of all of the all the one-step ahead states, and then get this nice effect we had in policy evaluation. What is preventing us from executing this equation? There's reinforcement learning, right? There's something in this equation we don't know. What is it? We don't know T. Actually, we don't know R either. Okay, so we can't run this equation because we don't know T and R. Okay, so in fact, the key idea is going to be that we're going to implement this equation, this update, that takes approximate values and replaces them with better values based on a one-step look ahead, but we're going to somehow do it without having to compute the average over everything that might have happened. We only get to know what did happen. So somehow we need to implement this average, this thing that says my value is an average of the one-step look aheads. Okay, so how are we going to do this update to V without knowing T and R? And the answer is going to be we're going to use the samples we experience to do the averages, just the same way that when we wanted to know the average age, we just picked some sample people and averaged them together. So the samples are going to come from our experiences. And you say, okay, but that's just a sample. It's the same with the age computation. We didn't check everybody. We just used the people we happen to have, and then we let kind of the laws of large numbers eventually do the right thing. Okay, so we'd like to improve our estimate of the value of a certain state, say it's S, by using the average of, and remember, pi is fixed here. So we're in some state, we've fixed an action, and there's just a bunch of things that might happen, and we want to average together all of their scores. And so what we're going to do is, because we don't know how likely each outcome is, the first idea is we're going to take the sample S primes by actually doing this thing and average them together. So we're in this state, and we have this kind of Expect-A-Max confronting us, but only one S prime is going to happen. Okay? So we get one sample. Okay, we take the action, and we end up in S prime sub 1. And we say we got a certain reward, and we can approximate the future using our existing values. Right, so that's an idea that we've had and we're now be able to use. So, but this is only one sample in that average. This thing that happened to us this one time is just one of the possible outcomes in that average. So if we wanted this average to be right, we're going to need more samples. We're going to sample another outcome of our action and another outcome of our action until we've got a whole bunch of outcomes of our action from this state. And for each one, we have an instantaneous reward plus a discounted approximate future. Now, if we had these n samples from this state, we could average them together, and that would be our new value. And this would be a sample-based way of doing this expectation, where instead of averaging things together according to the transition probabilities, we just take a sample-based average of the outcomes that happen. And it's that same idea. The things that have high weight in the transition function are going to appear more often as samples, and the right thing will happen in the limit. Okay, so on one hand, great. By taking samples rather than doing the average, we can now implement this update from policy evaluation. But I kind of broke something here. There's something very wrong with this algorithm. We have one more thing we need to fix. Does anybody see a flaw in this beautiful approach? Okay, so I'm in state S, and policy pi says go left. So I do it, I go left, and I receive a sample of what might happen. Okay, that was sample 1. How do I get sample 2? Do it again. Okay, go back. How do you go back? I don't know. We're in a reinforcement learning unknown MDP. I don't know how to go back, right? I didn't even know how I got where I got. So there's no way to go back unless you can rewind time. Okay, and maybe you can rewind time or maybe you can predict the future, but in general, this is not available to you. Okay, so the question is, how are you going to compute a sample-based average when you only get one sample? Okay, you might think, okay, that's easy, right? You just average it together. It won't be a very good average. So there's a big idea that says you can't just wait until you've accumulated enough samples from that state before you implement this averaging. You have to learn every time you take an action. And so every single action we take, every time we experience what's called a transition. A transition is when we experience a state, action, state prime, and then reward. Okay? Every time we experience one of these transitions, we're going to update the value of the state that we just left. So if I'm in a state and I go left and I land somewhere, I'm going to update my source state. S primes that are likely will over time contribute, but we're going to average them in as soon as they happen. Okay, what does that mean? Okay, the reason this is called temporal difference learning is that what we're essentially doing is we're saying, all right now I'm in a state, and I currently think the state is worth 50. Okay, now I take an action and I land somewhere. Maybe I land in a typical outcome, maybe I don't. Maybe it's a rare event. That'll all wash out in time. But I land somewhere. Maybe I get a reward of 10, and I land in a state that's worth 100. Well, I just got 10. I landed in a really good state that's going to give me 100 in the future, and looks like I'm on track to receive 110. But I used to think that it was only going to be 50. So I need to take that 50, and I have a choice. What do? I could clobber it with 110, but that's not right because the 110 may not be typical. So what I'm going to do is I'm going to kind of blend in the new experience. I'm going to average the new experience with all of my past experiences, which are encoded by the current approximation. Okay, so what we do is we're in some state, we act, and we receive a sample of the value, right? That sample is a real reward plus a landing state. Okay, so we have a sample of the value, but we also have our old value, right, which was the v pi of s to begin with. And so what we do is we average together the new sample and the old value. And we average them together in this kind of funny-looking way where we multiply 1 by alpha. You could think alpha here is something like 0.1, and the other by 1 minus alpha. That's like 0.9, so it's some linear combination. Typically, most of the weight is on the old value, right? So typically, alpha is something like 0.1 and not something like 0.9. Okay, and so what I'm doing is I'm constantly averaging in the new value with my old values, which are encapsulated in a single number. Okay, you can write that in a different way. You can write that the value is itself plus an error term, right? This error says how far off you are. And so you can think about this either as taking a running average or taking your current value and nudging it in the direction of the error, or rather the negative error. Either way, these are different only in algebra, and they're both useful intuitions to have. Yep. That's a great question. So if we're trying to average a bunch of things together, you would think alpha is some function of how many experiences I've had, right? And there's two ways you can actually cash that out. One is you could keep really kind of close track of, okay, I've seen 9 things. This is the 10th, and so the ones I've seen should have 9/10, and the one that I just saw should have 1/10. The reason you don't do that is because the one that you just saw is actually better than the old ones, because the one you just saw has in its computation a newer future estimate than these old ones that you saw 10 minutes ago. So this new one's actually worth more. It's more recent. So you want to give it a higher weight than it would get evenly. And this kind of update, even though partly it's just there for mathematical convenience, it gives you that effect, that newer samples contribute more. And also, you don't need to have phases. You don't need to kind of accumulate things until you switch to the new round. You're always running, and every experience you've ever had is kind of in the average, but with exponentially decreasing weight. So that's just just to repeat that in a different way. If you go around with a number, right, so if instead of taking an average of ages by adding up my 30 samples and dividing by 30, I said, all right, what's your age? And somebody says, I'm 23. I say, okay, so far the average is 23. Somebody else says, okay, I'm 22. Well, I take my 23, forgetting how many people led to it, I multiply it by 0.9, and I add 0.1 times the new one. Okay, at the beginning, right, this might make sense, but eventually the new people are contributing 0.1, even though the old people, you may have 1,000 people in the running average. This is not a bug, it's a feature. If you actually write out this update, you can see, you can rewrite this as a non-moving average, where you have averaged together every number that's ever contributed to the average, but kind of with exponentially decaying weight. And this is a feature. Everything contributes to the average, but with less and less contribution over time. So the old information kind of softly scrolls off the end in a way that you don't have to really track. Okay. The second part to your question is, in general, even though alpha is not going to be determined kind of in the obvious way, you do in general want the learning rate to decrease over time so this stabilizes. But then there's the fine print about alpha has to decrease, but it can't decrease too fast, and there's some fine print about that in order to make things converge. Okay, any questions on that? So let's do an example, and then we'll take a break. Let's do an example of temporal difference learning. So here are my states, A, B, C, D, and E, and also there's some terminal state X that we know is worth 0. And let's assume that the discount is 1, so we don't have to worry about tracking gammas, and that the update alpha is 1/2. You would never do this in practice, but it makes the math work out a little bit easier here for an example. So right now you begin, say, in this situation where, as far as you know, I mean, who knows if these numbers are right? You currently have a value for every state. You always do. They typically start out at 0. Right now, everything is 0 except for this one state D, whose value is currently estimated to be 8. Are they right? Who knows? Okay, so now we're going to do some experiences and change our numbers as we go based on each experience. All right, so the first experience we have is we are in B, as you can see with the red dot. The policy says to choose east, so we do. We don't think hard about what to do. We just do what the policy says because we're evaluating this policy. So the policy says go east, and we do. And this time, the result was we landed in C. And we got an instantaneous one-step reward of -2. All right, so now we have a little bit of a thought process. We say, on one hand, my running average of the value of B is 0. On the other hand, I just got some new fresh data in that says I just got a -2 and I landed in C. What's my total reward according to my approximation? It's -2 plus V of C, which is right now 0. So I think, based on this sample, that I'm going to get a total of -2. So on one hand, I have 0 representing the past, representing my past experiences, and I've got -2 representing my current experience, and I kind of average them together. Okay, so I land here. I do this update, where the old approximation is 0, the new one is -2 plus gamma times 0, and maybe if my learning rate is 1/2, I get a -1. Okay, so these are my new values. Notice that the learning isn't about the state you land in, it's about the state you left. When B takes me to C, I learned something about B. I don't actually know anything new about C. I found a new way to get there, but I don't know any more than I did before about whether it's good. I know something more about B because I just saw it lead to C, and there's something I know about C. Does that make sense? So even though it's a little bit subtle. You can think about, you move around and you kind of leave learning in your wake. You learn about wherever you left, not wherever you land. All right, so let's have another transition. From C, we choose the action east, because apparently the policy wants that. We land in D, and we receive a -2. So currently, what do I think C is worth? I think it's worth an average of 0. What does this experience suggest? It suggests I just got a -2, I learned in D, and what's D going to give me over time? It's going to give me an 8. So I'm getting a -2 plus the 8, which is a 6. That means I should now think that this state here is worth somewhere between 0, which is my old information, and 3, which is my new information. and 6, which is my new information, and if I average those evenly, then it will be a 3. So you can see that as I move, each experience rolls into the value approximation I have at the state I just left. Okay. Quick sanity check. If my policy continually throws me into the pit of death, are the values going to be high or low? They're going to be low, because I'm going around saying, oh, this is bad, bad things are happening, and I'm writing down essentially what's happening to me. So the values you get depend on what you do, right? If you act well, you're going to learn good values. If you act poorly, you're going to learn poor values, and that's actually what you want, because this is policy evaluation. You learn about the policy you're following, and that makes sense here. Okay. Let's take a break, and then we'll look at the problems with this, and then see kind of the core algorithm we're going to use going forward, which is an algorithm called Q-learning. Okay, let's get started again. Okay. So we just learned a new algorithm. What is this new algorithm? This new algorithm goes along and for each state tracks a value, right? I mean, kind of value iteration did this, policy evaluation. All our algorithms basically kept approximate values sitting around for all the states. This one is no different. The only thing that's different now is that rather than doing sweeps where you go to each state and compute some expectamax in order to find the new value isn't based on an expectamax, it's based on a single experience. So instead of the new value clobbering the old value, it's kind of blended in as you go. Now, there are two issues. Kind of one is like a data structure issue, and the other is a more subtle issue. The kind of just structural issue that's a problem with this value learning algorithm is while it is a model-free way to do policy evaluation, right, essentially doing the policy evaluation algorithm in a sample-based way, it doesn't really work in a context where we have to actually act. We didn't design it for that. It was for passive learning. But when you have to act, remember, you have to choose an action according to a policy, right? So far we imagine that our policies were given to us. But if we had values and we needed to compute a policy, well, remember, it was easy to choose a policy from Q values. You would look at your state, you would look at its Q values, and those were the score you'll get for each action. And you pick the action that gives you the highest score. But the problem is the Q values can't be derived from the values without this kind of Q value update equation, which we can't do because we don't know TNR. Okay, so the idea in terms of just the structure here is if we want to act, we really shouldn't be learning values, we should be learning Q values. So we're going to have an algorithm in a minute which is called Q-learning, which is going to learn Q values. But there's actually another subtle problem with this algorithm we just saw. Remember we talked about if you kind of continuously jumping off the cliff, you learn that all of the states are bad? Well, we'd really like an algorithm that rather than learning the values of the policy that you are executing, it learns the optimal values. And actually, people for a while weren't even sure this was possible, right? This was kind of the big holdup in reinforcement learning for decades, was trying to find a way that let you learn not the values under the policy you're following, but the optimal values. So you're like throwing the robot left and right off the cliff, but occasionally doing something smart, and somehow learning that the values are actually pretty good, because although you've been jumping off the cliff, under the optimal policy you wouldn't be doing that, right? And so we'd like to solve both of these problems. It's easier to kind of think about solving the problem of learning the Q values, and we'll see along the way how it solves the more subtle problem at the same time. Okay, so active reinforcement learning. This means the robot doesn't know what happens when you jump off the cliff, so it does it. It maybe has to do it a lot of times, and it maybe has to jump off the cliff from every possible point, because you only learn about the things you do. Now, of course, as we kind of flesh out the ideas of reinforcement learning, eventually you'd like to learn that if one cliff is bad, they're all bad, but today there's nothing like that. That won't happen until next lecture when we start tying states together using features. Okay, at the moment, you got to try everything, which means you actually incur the loss in the real world, and that means that slowly over time you're responsible not only for exploring and trying a bunch of things to learn, you're also eventually responsible for doing the right thing and not just constantly incurring losses. So in full reinforcement learning, okay, we're going to traffic in optimal policies, just like value iteration. So what we'd really like to do is implement the value iteration updates somehow using samples, though we'll see it's very hard. Okay, so we still don't know the transitions, we still don't know the rewards, we are going to choose the actions, And our goal is to learn the optimal policy or the optimal values, and we're going to kind of do those at the same time, just like value iteration did. The learner is now making choices. So we have this fundamental trade-off between exploration and exploitation, right? Should we try something that's probably bad just to be sure, right? In order, basically, do we do things for science? Or do we just kind of go with whatever looks best now, which is going to give us higher returns, but actually cause us to learn less? And there's a trade-off there. We'll formalize that trade-off going forward, though it's going to take a couple different topics in the rest of this course in order to get all the pieces of that. Okay, it's not offline planning. You're not thinking deep thoughts. You're actually trying things in the world, and then slowly over time trying to do the smart ones. Okay, so we're going to do a little bit of a detour. Let's remember what value iteration did and why we can't just approximate it with samples. So what was value iteration? Right, okay, this is a really, I'm gonna write the equation out because this is really important. This is the key idea behind Q-learning, right? If I wanted to compute an approximate value for a state S, and I wanted to base it on what is going to happen in one time step under optimal actions, I would say, well, that's going to be a max, right? I have to take a max over all the actions available to me, because I'm doing action selection now. And for each action, if I knew the MDP, I would say, well, I have to take an average over all the possible outcomes. I weight the outcomes according to their probability. That's the transition function. And for each outcome, the value is going to decompose into a one-step reward, the instantaneous reward, plus a discounted future value, which I plug in my approximation, which for value iteration came with a subscript k, for the landing state S prime. So that is the value iteration update. Okay, the thing we can do with samples is we can mimic averages, right? We know this. If I want to average all the ages, I just grab a couple samples and add them together, and that's going to do an average using samples. It's easy to do averages with samples. We don't know how to do maxes using samples, right? There's no real sample-based max. And people stared at this equation and they said, I can crack this, right? I don't need to know t in order to compute that sum. I can just take samples of the things that are happening. But I don't know how to take a maximum over actions without actually having the options and explicitly choosing the biggest one, right? Nobody knew how to push the samples through the max, okay? And the key insight was that values, though they're the intuitive things, are not the only quantity there is. So here's the value iteration update. You could also do one-step look-aheads on the Q values, right? Nobody likes Q values at first because they're a little bit weird. Q values are weird. They're states paired with a specific action. But they answer the question, what is my score if I take this action from this state? So on one hand, they're actually more useful. You can use them for action selection. And secondly, let's write down the one-step look-ahead. Well, the one-step look-ahead, if I started a chance node in an Expect-a-Max tree, I have to consider the possible outcomes. And then for each of the outcomes, I would need to consider the possible actions. And then I would be back at a chance node. So if I unroll one layer, kind of half apply off here, what I would get is I would get an update that says, well, if I want a new approximation to a Q value for SA, what do I need? Well, I need to consider an average over all of the S primes that will happen. Okay, I would need to weight them by their likelihood. Then I would need to add in the instantaneous reward plus a discounted future reward. But here's the thing. If I'm writing Q's in terms of Q's, I can't write V here, right? I can't write V. I just did. But you can't do that because you don't have the V's. If you want to reduce it to Q's, I have to write it in terms of Q's. Well, what's the value of a state in terms of the chance nodes below it? It's just a max of all of the actions, A prime, of the Q values from the landing state S prime, like that, okay? So now I wrote Q's in terms of Q's, and all I did was I shifted my one layer of Expect-a-Max a half step down the tree. So it's chance nodes in terms of chance nodes. It's got the same ingredients. There's an average over outcomes, there's an instantaneous plus future, and then there's a maximum over the actions. It's the maximum that makes it optimal. Okay, but now something really nice has happened. Because the Q values break my memory, because they break my approximation up by actions, I can compute this explicitly whenever I need to by just looking at the Q values and picking the biggest one. And the outer thing is now an average instead of a max. And because the average is now on the outside, I can now approximate the Q updates even though I couldn't approximate the value updates. And so this was the big breakthrough in reinforcement learning, is the idea that if you make Q's the outer quantity, suddenly this equation you want to mimic with samples is an average and not a max. Okay, so we would like to do this equation as we go based on samples. So here's how it's going to look. Okay, we're going to learn Q values as you go. They're going to look like this in grid world. So I'm going to bring this up in the GUI in a second. But they're going to look like this. So for each state, you're going to learn 4 numbers, if it's the kind of state that has 4 actions. They're going to all start at 0, and we're going to learn them all as you go. So what's going to happen is you're going to get a sample. You're in some state, you choose some action, you land in S prime, and you receive a reward R. And you're going to go through the following reasoning. On one hand, until I received the sample, I thought my starting state S and my starting action A were worth Q of SA. So I thought that this combination of S and A was going to lead to QSA as my score. But now I've just gotten a new estimate. My new estimate is the reward I just got plus the estimate at the landing state, which has got this max embedded into it. So I have to look ahead at the state I land, and in order to figure out what's going to happen, I have to consider everything and take a maximum. If you think about it, that's like looking at my landing state and saying, not what are you worth under the current policy, but what are you worth if I do the best thing I can locally, right? And so this sample is something like a one-step look ahead with a little bit of expect-to-max kind of optimality built in when you max over actions. So I've got my old estimate of the Q value, my new estimate of the Q value, and I do the same thing I did before, which is I take a running average with this kind of linear weighting. So 0.9 times the old value plus 0.1 times the new value. Let's see this. We're going to see this twice, because this is kind of the key idea here in reinforcement learning algorithms. So let's take a look. Let's first take a look at which one do I want to show you? Let's do this one. Okay, so right now all the Q values are 0. And I'm going to move, and as I move, the Q values will start to update. Okay, the parameters here are that the living reward is 0, meaning in general, when I take that first action, it's like I thought it was worth 0, I got 0, I landed in 0. Nothing really happens at the beginning because everything's 0. The only non-zero rewards in this MDP are at the exits. So as I move, nothing interesting happens until I choose the action east here and land in the pre-exit here. Now, as I land here, nothing actually happens because I still get a 0. But from this state, I'm going to take the exit action. I'll be airlifted out, and I'm going to receive some reward. I think the reward here is +1. And I start over again. Okay, so I start learning more. Now, why is it 0.5 and not 1? I just got a 1. Why didn't I write that down? Because my old value was 0, my new value is 1, and I average them together. In this case, the learning rate is apparently 0.5, which again is nice for demos, but kind of probably a bad idea in the real world. Okay, so now I move again and again and again, and nothing happens until I'm here. Now, when I move east, I'm going to say my Q value, which is the 0 right here, okay, I'm going to say I used to think it was worth 0, and as I move east, I'm going to land in a state which is worth 0.5, and I'm going to say, well, 0, 0.5, I'm going to average them together, and what's the Q value going to become on the east slice of the pie here? 0.25. Okay, so, and then as I leave, I kind of average 0.5 and 1 together, so that goes up to 0.75. So I'm just going to keep walking this path, and you can see, is something going to happen here when I move? Okay, I think east is worth 0, and as I land, I'll discover it's worth 0.25. Okay, and I'll average them together. So I'm just going to manually do this a bunch of times. And you can see it takes a while for things to propagate back. And because the learning rate is 1/2, it takes a while for those 0.5s to kind of go towards 1. But let's look at several things that are happening. One, I'm only learning about the actions I'm taking. That makes sense, right? I'm going to start doing some other things. So first of all, if I go here, if I go left, okay, I go west, what do I currently think west is worth? I currently think it's worth 0. I'm going to land, let's say I land to the left. What is my landing state worth? It's worth 0.98, so essentially 1. So I should now think that west is worth 0.5, which happens. And notice I learned something about it that is backed by the knowledge that when I act optimally from this current state, it involves going east twice and then exiting. So I learned something in one step that's backed by all of these other experiences from other runs. Okay, so that's nice. It lets me learn a lot faster. And let me show you the optimal thing. What's the best way to do this? Okay, so let's go around the other way. Let's say I decide to start acting dumb. And I start taking this wonderful path and using it to jump into the cliff. Okay, let's look at what I'm learning. Okay, obviously from here I'm learning that the east action is bad, right? But notice what I'm not learning. I'm not learning that this state is bad, right? Because even though I'm doing dumb things from it, right, the only thing I update when I go south is the Q value to the south. This doesn't mess up my knowledge of the other actions. And moreover, even though every time I go to the south, I kind of fall into the pit of death, notice that the Q value for south is still 0. Because even though when I go south, apparently there is an action that's bad, the Q value update tells me to approximate the future using the best value from the state. So it considers this state with a minus 0.69 to be worth 0, right? Because it assumes when I land there, I'll act optimally, even though I don't, right? So it's telling me something about optimal action, not about what I'm actually doing. Okay, so if I go back and forth between these, I'll start to learn that, in fact, going south from here is pretty good, because if you act optimally, you should go back north and then go out the good exit. Okay, so what's neat about this is we're learning about the things we try, and somehow the learning isn't affected by the experiments we do, right? We learn about optimal things, and that's because of the max in the equation. Okay, let me show you another version of this. All right. This is, well, let's see what it is. Oh, it's flickering. Pretend it's not. Okay, so look at this. What do you think is shown on the bottom in the giant flickering mess? Yeah, so these are states down at the bottom. It's a two-dimensional grid because the state space of this robot is 2 angles, one for each part of the arm. And green and red here are relatively good versus relatively lower values. Values are shown on the left. Q values are shown on the right. You can tell that because you've got 4 actions from every state, and they're kind of in quadrants. It looks a little like grid world, but this is not a grid world. And you can see we're learning about the stuff we try. Okay, what about kind of down here? We don't know anything about it because we haven't tried it. So let me skip into the future. If I skip far into the future, suddenly you'll see that I've now learned about all these Q values. Okay, so one interesting thing is notice we don't go to the bright green. I guess I need to click a couple things down so you can see for a second. Okay, so I'll tell you in a minute what I did just there. But notice we don't just go to the bright green and sit there, right? Because the bright green states give you a lot of future returns, but they do it by moving towards worse states and receiving instantaneous rewards along the way. So you don't just like sit at the good state. You do the good policy. And that's shown by the little blue lines over here. Okay, if I stop this and I displace it, right, even though it's not supposed to get here, it'll kind of do the right thing and get back on track because it's learned the whole policy. Okay, we'll stop the flickering. Okay, so we learn Q values as we go. Let me tell you about some properties of this algorithm, and then we've got a couple high-level things to talk about, and then that'll be today. So there's this amazing result. Q learning, this algorithm, converges to the optimal policy and the optimal values, even though you aren't following the optimal policy. This is kind of amazing. It's something called off-policy learning. You don't learn the values for the policy you're executing. You learn the optimal ones, even if you're not following it. With value learning, you would have had to follow the optimal policy in order to get optimal values. There's fine print, right? You're not going to learn unless you explore enough. You're not going to be able to learn about states and actions you don't take. You got to make the learning rate small enough, but not too small. But kind of if you get all the fine print right, in the limit, you can select actions completely at random and you will learn the optimal policy. Okay, you don't want to select actions at random in the process of learning the optimal policy. Why? Why don't you want your robot just kind of moving around at random? It'll work in the limit. Okay, but one, it's going to take a lot longer, right? And two, you're going to lose a lot of robots in the process. So your regret, formally speaking, will be high. Okay, so this is kind of you know from a lot of these kind of decision theoretic concepts, you know them from life, and we're just kind of formalizing them in some way. Here's this trade-off between exploration and exploitation. You have your place that you like to go to eat food, and it's tasty. And there's this new place, right? Is the new place better than your favorite place? You know, probably not, but it might be, right? So you go and you try the new restaurant. And let's say you have a kind of mediocre meal. Do you go back? Maybe once. Maybe you wait a while and go back. So you'll do a certain amount of taking actions, which you think probably are not going to immediately reward you, but you do them for science, right? You do them to learn, to gather information. Okay, there's other things in the restaurant analogy. Maybe you enjoy something new. That's kind of secondary stuff in this metaphor. But the key idea is you take actions also for the sake of learning. So how are we going to get our reinforcement learning? The Q updates are just whatever policy you're following, it kind of does its updates. How do you know what actions to take? Well, there's a bunch of schemes. We're not going to cover everything you might do. And in fact, to formalize the optimal thing to do is going to require machinery we're not going to have this week. But the simplest thing you can do is do what's called an epsilon greedy exploration policy. This says every time step with some probability, epsilon, take a random action. With a much larger probability, 1 minus epsilon, follow your current policy. This says your robot should do its thing, but occasionally just like jump off the cliff for kicks, right? Is this good? Well, you know, you don't spend all your time exploring, so that's good. But on the other hand, when you do explore, it's kind of unfocused. So there's problems with this. You eventually explore, but you kind of, even once you're exploring, you keep thrashing around. If you remember, I was doing something to stop the exploration in that applet. That's what I was doing. It was an epsilon greedy policy, and I was lowering epsilon so that you could see just the greedy behavior. Okay. You can kind of lower epsilon over time. There's other solutions. I'm going to sketch one right now, but the exact form is actually not super important. If you want to know when to explore, you should really be taking random actions kind of maybe at the beginning, but what you want to do over time is explore areas whose badness is not established. When you decide to try a new restaurant, you don't pick a restaurant at random. You choose a restaurant that you don't know much about, but maybe your prior belief says is reasonably promising. So you use exploration functions of some kind. One way to formalize that is to say that rather than in the Q update, and again, the kind of immediate, the detail is not as important as the idea, rather than approximating the place you land with its current Q value, you can kind of take the current Q value plus a count of how many times you've been there and upweight Q values of places you haven't been. So essentially, you treat states that take you to unknown territories as being a little bit better than they are until those territories become unknown. And this can give you a nice behavior where on that robot, for example, you would learn very quickly. Let me see if it'll behave. All right, so this is that GUI. Now it's exploring, but it's got an exploration function. So it stops exploring as it becomes confident. And okay, it's a little weird, but it's basically done. Okay, so rather than having to skip a million time steps and still watch it thrash around, you can see that it's actually still got some epsilon in it too, so let's take that out. Oh, I guess we can't take it all out. Anyway, you get the idea. You can learn much faster if you basically just damp down the exploration once it's no longer needed. So that can save a lot of time. Okay. So in conclusion, okay, lots of new ideas today. We now know how to do a lot of different things, and they each have algorithms that actually look a little similar. If you know the MDP, you can compute optimal things with value iteration. You can evaluate a fixed policy with policy evaluation. When you don't know the MDP, we can learn the MDP, that's called model-based reinforcement learning, or we can do policy evaluation in a model-free way, that's called value learning, and we can learn optimal Q values and therefore policies with this algorithm we just learned called Q learning. So that's it. Next time we're going to see how to deal with large spaces where you can't enumerate the states, like Pac-Man.